All right, guys. This week we are moving on to section 1.4. We are getting close to the test. We only have one more section after this, so about 2 weeks we will have our first test on all of chapter 1. But this week we are focusing on testing a hypothesis. Remember, that is one of the steps of the scientific method. Last week we talked about the scientific method as a whole, and we briefly mentioned testing a hypothesis, but we did not talk in detail about it. So this week our focus is solely on testing a hypothesis. When we test a hypothesis, there are 3 different ways to do so. First is observation. That is when you do something that is only using your senses. Second way is experiment. That is when you test the effect of one thing on another using controlled conditions. And we'll spend most of today talking about this one. And then there is using models, which is something created to help you understand the idea or concept better. Okay. Observations. This is simply using your 5 senses that you learned way back in kindergarten to observe the item or the phenomenon. So you can see, you can hear, you can taste, you can touch, and you can smell. Most of the time, we are not going to taste in lab, so please do not do that unless specifically given instructions by your teacher that it is okay. Please do not taste anything this week in lab. We don't want you to ingest any of the chemicals that we will be dealing with. Okay. If you are making an observation, okay, in quotes, but you are not using one of your 5 senses, it's called an inference. And an inference is a conclusion drawn based on past experiences. And that's not necessarily a bad thing. You don't have to touch the oven or the stovetop while your mom's cooking pasta to know that it's hot. Okay, you can see it glowing red, you see the flame if you have a gas burner, and you know it's hot. Probably based on, as a young child, you either touched it or every time you got close to it, your mom would yell at you to not touch and yell hot. So inferences are not necessarily a bad thing. Okay, but in science, when we are making observations, we have to get rid of inferences. We do not want them. If we cannot see it, we cannot hear it, we cannot taste it, we cannot touch it, and we cannot smell it in the present sense, then you cannot write it down as an observation. Okay. Next, we're going to talk about experimentation, and here's where we get a lot of vocabulary words. So you may want to make index cards this week of these vocabulary words because there are a lot of them. Okay, first off, variables. Variables are quantities that can have more than one value. Okay, so last week, toilet paper was a variable. Okay, we had brand A, B, C, and D. Okay, the pennies were a variable. Okay, how many pennies would that brand of toilet paper hold? Okay, when we have variables, we put them into 2 categories. The first is an independent variable. Independent variable is what you as the scientist change or manipulate to see how something else is changing. So when you think back to lab last week, we had the variables of the toilet paper and we had the variables of the number of pennies. What is the item that you specifically as the experimenter changed? You changed the type of toilet paper. So that was the independent variable. You changed it. The other type of variable is a dependent variable. And those are the things that are affected because you as the scientist changed something. So if you, again, you think back to our lab this past week, you changed the brand of toilet paper. The result of that is the number of pennies may have changed for how many pennies that toilet paper could have held. Okay, another common variable that we will be dealing with is time. Okay, time 99% of the time is the independent variable. Okay, time keeps changing regardless of if the dependent variable such as temperature changes. So as we go throughout the day, time changes, temperature might not. Okay, one example of when the time might be the dependent variable if you were testing battery life. Okay, so I have 4 or 5 different brands of batteries, and I am running them to see which battery runs the longest. Their time would be the dependent variable based on which brand of battery, the independent variable. A little bit more about experimentation. With experimentation, you need constants. Okay, definition of constant, something that stays the same during an experiment. Think back to the toilet paper lab from this past week. What was a constant in this lab? A couple of constants. Use the same beaker for each trial. Okay, you had the same number of drops of water in each trial. Those things did not change from trial A, B, and C and brand A, B, C, and D. Those things stayed the same. Okay, you also need controls. Controls are something that you compare your results to. For example, our toilet paper lab for this week, what did you compare your results to? Okay, in that lab, you compared your results to each other. So the control was built within the experiment itself. If we were looking at A, we compared it to B, C, and D. Okay, if we were looking at C, we were comparing it to A, B, and D. Okay, most of the time, it is where the independent variable is not changed. Okay, sometimes it's a known or accepted value. So let's look at this first one, usually where the independent variable is not changed. So if I wanted to test the effects of fertilizer on plant growth, okay, a good hypothesis was if my independent variable, fertilizer is applied to plants, then dependent variable, plants will grow taller. Okay, so fertilizer is applied, plants may or may not grow. That's what we're testing out here. My independent variable, fertilizer, dependent variable, height, okay, whether it's in centimeters, meters, whatever, of the plant. Okay, when I'm running this experiment, I'm going to have a couple of plants that do not get fertilizer. Everything else is held the same. I'm going to water all the plants exactly the same. I'm going to give all the plants the same amount of sunlight. All the plants are going to have the same type of soil. The only thing that can be different in this lab is the fertilizer. Okay, the other one, sometimes a known or accepted value. Okay, example of this would be the known acceleration due to gravity. Okay, it's a known value. So we can compare how our objects fall, calculate that acceleration due to gravity, and see how our results compare to the given value of that acceleration. Okay? Whenever you are doing an experiment, you must make sure you record accurate and precise observations. Okay, it was important 2 weeks ago. It isn't important today. It's going to be important 2 months from now. Okay, you've got to make sure you are recording your observations when you make them and making sure you are making accurate and precise measurements. One thing that comes in a lot of time with experimentation is bias. Okay, bias occurs when what the scientist expects changes how the results of the experiment are viewed. Okay, we had that definition last week. How can we reduce bias in our experiment? Okay, we can run lots of trials. The more likely our results are to be. Okay, making sure we make careful and complete observations, recording everything we see and observe. Reporting both the pros and the cons, okay, not leaving any data out. Make sure our data is measurable, okay, does it have a value in a unit attached to it? Okay, would someone else come along and make that same measurement? Okay, and then finally, make sure that the experiment that we're running is repeatable by others. That way, someone else that doesn't have that bias towards the experiment would get the same results. However, even in the best situations, some experiments may contain some bias. It's just going to happen, but we try and eliminate it as much as possible. Okay, next up is models. Okay, models represent an idea, an event, or an object to help people understand it. Models can be computer simulations. They can be something that we build in class to help us understand it. Okay, models are used in science to study stuff that's too big, too small, or too dangerous to study. Okay, those simulations, okay, when we're trying to figure out the path of a hurricane, we're not going to go into that hurricane and figure out exactly how the wind is going. Okay, we have computer models that can see how that hurricane has formed and what the path it is right now, and it's going to compare and run mathematical simulations to project where that hurricane will go. Lots of different models out there. We use models to study the ocean. We use models to study earthquakes and tsunamis. We use models to study astronomical features. Okay, we use models to study the cell. Okay, so lots of models out there. Okay, those are just a few of the examples that we have. Okay, finally, we need to talk about this idea of theory and law. Okay, theory is an explanation of things or events based on knowledge gained from many observations and investigations. Big word here is explains. Okay, it's based on knowledge gained. Theories can change, they are not set in stone. As we develop new knowledge about a topic, we can adapt that theory to reflect that new knowledge. Okay, it's going to explain why something happens as well. Example of a theory, not one that we are going to study in integrated science, but if you go on and take chemistry, you'll study atomic theory. Okay, that tells you how the atom is composed, what it looks like, that structure. At one point in time, atomic theory described the atom as a plum pudding model where everything's kind of evenly spread out. Okay, then we kind of learned new knowledge based on some technologies that were created, and we came up with this kind of solar system atomic model that you're used to seeing. Okay. Over time, we have actually learned that electrons live in orbitals, and that atomic theory has been changed yet again to reflect that new knowledge. Okay, theories also explain why something happens. Okay, there is a theory on gravity, gravitational theory. This tells us why objects are attracted to each other. There are also scientific laws. These are statements about what happens in nature that seem to be true all the time. It usually takes a long time for something to become a law. It's not, oh, I discovered this, it's true, it's a law. Okay, it's going to tell us what happens. Okay, Newton's laws of motion tell us how an object's motion is going to change, if it's going to change. Okay, big thing is theories don't become laws because whys can't turn into whats. Okay, I can't have the answer to a why question suddenly become the answer to a what question. So we can have theories and laws about the same general science concept because a theory is going to tell us why it happens, where the law is going to tell us what happens. Okay. Next thing, and we've already touched on this a little bit way back in section 1, but a lot of scientific experimentation and modeling leads us to some technology. So it's important again to realize science and technology are not the same thing. Science is that knowledge done to gain knowledge about that natural world. Okay, we learn how it's ordered. Key thing here though is it's about the natural world. Okay, those three branches of science that we talked about. Technology is the means of solving practical problems by applying that new knowledge that we may have gained through science or even engineering. Remember, engineering is that problem solving. Okay, science might present us a problem, engineers try and figure out how to overcome that problem, and in the process may create technologies. Okay, technology does not always follow the science. Okay, we have lots of technology out there, but that doesn't mean that we should use it. Okay, we have nuclear technologies, we have genetic technologies. Okay, there's lots of different technologies out there that kind of raise this ethical, moral issue of, yeah, we can do something. Yes, we can launch a nuclear warhead at another country, but that doesn't mean that we should. Okay, so we have to play this ethical, moral game with ourselves. Okay, yes, we can genetically change an unborn child before conception, okay, and give it the DNA that we want it to have, but does that mean that we should? Okay, just a few of the types of questions that are raised when that line between science, engineering, and technology becomes very blurred and we get technologies that are created and on that cusp of the forefront of where we're going. Okay, that concludes our notes from today. Please make sure that you have answered all the questions regarding this, and then you need to go and get your lab notebook set up. Make sure you read the lab, make your copy. Okay, make sure you are changing the name of that lab to be the format that it's supposed to be, name of the document, your hour, and your name, and then make sure you go online and answer that lab entry ticket. It is going to be extremely important with this week being homecoming and Friday being a shortened period that you guys are ready to work in class tomorrow. Read through the background of the lab, read through that procedure, get that couple of data tables, I believe there's 3, into your lab notebook. You don't have those ready to go, you're not going to do lab on Thursday, and you're going to have to be making this up, which means study halls and after school. And I don't think you want to be after school on Friday after the parade making up labs. So make sure you come to class on time and ready to go tomorrow. Have a great day.